Okay, so let's talk about chapter 26, galaxies. Okay, so we're going to talk about the discovery of galaxies, the different types, properties, different scales, and how the universe is expanding. So until 1924, we weren't sure that the Milky Way galaxy was a galaxy and there were other ones. Up until 1924, we thought that there were the other nebula in our when we take pictures of the sky were within our Milky Way galaxy, and that was all there was. But in 1924, that all changed when Edwin Hubble measured the distances to Cepheid variable stars in Andromeda galaxy. He found that, well, he estimated using his own measurements that the um, Andromeda Nebula was about 900,000 light years away, which was further than any other star had been measured in our own galaxy. So that allowed him to uh, publish this paper, which um, resulted in a standing ovation at a meeting where he announced his findings because it was a major, major discovery that the Andromeda galaxy pictured here is a completely separate galaxy distinct from our own, revolutionized our ideas of the universe. So the main types of galaxies are elliptical, spiral, and irregular. Those are the three you need to know. And we're going to talk about the different types. So we've talked about our own galaxy, which is a large spiral galaxy. It has a bulge at the center, spiral arms coming out of the side, and all of that is a part of the disk. And then there's the overall halo, which is a large sphere around the galaxy. Okay, so here's uh, an example of the same, not the same galaxy, but a similar galaxy when viewed edge on, where you can see that's the disk, there's the bulge, and then this would be the halo all the way around it in a big sphere. Okay, and we've got another galaxy here, disk, bulge, halo, and so on. Okay, so this is what's called a barred spiral galaxy. So some galaxies are just spirals, where they spiral out like that, and some have this bar shape in the middle. So you think of it like a bar that all these aliens would sit at the table and you're at the bar and get a drink or something like that. Or a ballet bar and you've got a bunch of alien ballet dancers and they're all standing along this line. And then the spiral arms continue from there. So there's just two types of galaxies, spiral and barred spiral. Two types of spiral galaxies. Okay. The This is the Hubble classification of galaxies here. So the full spread of galaxies are there's elliptical types of galaxies, which look like a football, and then you have spirals and barred spirals. So in terms of number of spiral arms, you'd have SA, SB, SC type of classifications. And let's see if they talk about that here. Blah, blah, blah. It should, yes. I'm trying to see where they say this. Yeah. Okay. SA, classification by shape. So SA, SB, SC, those are the types. Ellipticals go from pretty circular to pretty elliptical from their scale, starting with E, and then barred spiral A, B, and C, depending on how barred it is. Okay, so elliptical galaxies, they have a gold color like this because they're usually older and they're usually quite large. Um, so you have to know the difference between a spiral and an elliptical, the different little types of galaxies and what their properties are. Irregular galaxies are just, uh, they don't have a really defined shape. Some examples are the large and small Magellanic Clouds, which are actually in our own galaxy while they're actually orbiting just outside, but they will merge eventually. And they're irregular dwarf galaxies, and they're on their way to being eaten by us. Um, so yeah, there's evolution of galaxy. The main ideas, we'll talk about these in the future, is that collisions and mergers between galaxies change spiral galaxies into elliptical galaxies. So we generally think of elliptical galaxies as older, larger, having gone through many collisions before in their histories. They don't have a lot of active star formation, so they end up looking a little bit more gold. As far as properties of galaxies, um, we try to estimate their masses by looking at the number of stars that are in them. We estimate, as well as the orbits of the stars. We estimate that there's about 400 billion stars in our galaxy. Um, and It says here Milky Way is turning out to be somewhat smaller than Andromeda. I don't know if that's still the case. I think Andromeda and Milky Way are close to each other in size and mass. Even more recent developments. Okay, so here's your characteristics. So ellipticals have a little bit larger range, but tend to be more massive. Irregulars tend to be less massive. The diameters, ellipticals can be just absolutely massive. Irregulars are usually pretty small. The luminosities can be very bright for an elliptical. Spiral galaxies can be pretty bright too. But ellipticals can also be very dim, and irregulars can be pretty dim too. Spiral galaxies have a mix of old and young stars. Ellipticals are primarily old stars. Irregulars can be both. And um, elliptical galaxies, excuse me, I got a cat here in my throat or something. Okay, interstellar matter, sorry, elliptical galaxies have almost no gas and no dust, so they don't have active stars. That's why they don't have young stars in them. Um, the Yeah, this is mass to light ratio in the visible part. I don't think you need to worry about that. Yeah, we don't care about the other two. Okay, so yeah, you can kind of skip through this, but you can read this. Okay, this is a beautiful galaxy, the Pinwheel Galaxy. Okay, so the extragalactic distance scale, we want to describe how we use Cepheid variables and standard candles to estimate the distances to galaxies. So you remember variable stars have a intrinsic luminosity, which depends on its volume. Sorry, not volume, luminosity. So depending on its variability and how quickly or not quickly it blinks, we can get the mass of the star. And so here's an example of a star that's changing brightness as it goes about its day. So we call them standard candles. Another standard candle is a type 1 supernova. And remember, standard candles just mean we know how bright they should be, and so depending on how bright they appear, that tells us how far away they are. So we can estimate the distances to these things based on their brightness. This is a really wonderful image of a star going supernova, and it exploded, and it's part of this galaxy. And just look at how bright it is. It's brighter than any other point in this entire galaxy. That's crazy, right? Okay, oops. Okay, so okay, so blah blah blah. So I'm trying to see if there's anything here. Planetary nebula, Cepheid variables. So these are the distances you can get to objects using standard candles. So the furthest you can get using kind of our standard things are hundreds of millions of light years. But with type 1a supernova, you can get billions of light years away. And then Hubble's law allows us, by measuring the redshift of a star, to get all the way to the edge of the universe. The Hubble law is talked about here. So Hubble law is a relationship between the redshift of a galaxy and how far away it is. And so what Hubble started doing, and there he is. No, that's Milton Humiston. What he started doing was measuring the redshift of galaxies. And then what they were trying to do is estimate the distances to galaxies using the variable stars and other things. And then comparing the redshift to how far away they are. And what they found was the data fit a line. And the line is that the further away a star is from us, the faster away it's moving from us. And so that the implication of that is that the galaxy is, or the universe is expanding. And so you can see expanding this data set out to even further and further to, this ends at 6 million light years. This one ends at 120 million light years. And you can see that there's a very nice relationship between the data, the distance, and the recession velocity. Okay, so what that means is that, this is the velocity. This is the distance. Y equals mx plus b. You might remember that. Y is velocity. Slope is m. X is distance. So then the slope we call h, the Hubble constant, and that's what this equation is here. And it just allows you to say, okay, if you're this far away, poop, you can just multiply by h and you get your velocity distance away. Or if you measure your recession velocity using the Doppler shift, you can divide by v and you can get the distance right away, how far away the galaxy is just from that relationship. So that allows us to figure out how far something away is just from the Hubble constant. Okay, and then that's it. And so Hubble's law then allows you to estimate the expansion of the universe and how far away things are, just by looking at the redshift. So this is an example of the expanding universe. So we'll talk about this in lecture, and I've got some good demos that show how this works. But basically, the universe can be expanding without, the galaxies themselves expanding. And so we'll try to explain this in a little bit better way than raisin bread or something like that, to show you how the expansion works. But this was the first evidence that the universe was expanding, was that if you looked at the Type 1a supernovas and the Doppler shift and compared them, you found that the redshift was more redshifted the further away the object was. So this velocity measurement here, that's basically the redshift. The faster it's going, the more red it looks. And so you can get that redshift. This is sometimes written as z, the redshift on the y-axis, and the redshift is a function of, the amount of redshift is a function of the distance. The further away it is, the more redshifted it is, which means the further away it is, the faster it's moving, and it tells us the speed, how far away it is, and which tells us that the universe is expanding. So we'll talk about this expanding universe stuff tomorrow. Well, not maybe tomorrow by the time you read this, but or watch this video. But anyway, bye. Let me not say bye yet. Let me go over the summary. So in summary, 1924 was the first year, less than 100 years ago, that we realized that the Andromeda galaxy was a completely different galaxy, and that the universe was filled with galaxies. And the Milky Way wasn't the only game in town. There's 3 types: spirals, ellipticals, and irregulars. Make sure you know the differences, and they're all just based on cosmetic differences, but they actually, those cosmetic differences tell you a lot about the different structures and properties of the galaxies. The properties are masses. This is the main thing we do is we measure the mass of a galaxy and try to compare them from that. And then we look at the mass to light ratios to try to estimate the star formation in them. The extragalactic distance scale is using Cepheid variables, standard candles like Type 1a supernova, the Tully-Fisher relation, which has to do with the 21 centimeter line and the luminosity of the galaxy. They each have their limits, so that's a key thing, that Type 1a get us pretty far, further than the other things, and that the redshift from Hubble's law can help us get all the way to the edge of the universe. And Hubble also discovered that the universe was expanding once he discovered that Andromeda was outside of our galaxy, he started trying to measure the distances to other galaxies, and then compared that with the redshift and discovered that there was a relationship. The further away the galaxy is, the faster it's moving away from us. And that led to the implication that the universe is expanding. Okay, bye.